Hello everybody, yet again to a second video, paper 2 from 2021 Edexcel's A Level Pure paper. So we've done paper 1 of the Pure section, now it's on to the second paper. So similar idea, but obviously different topics which haven't been assessed yet on paper 1. So I'll get straight to it and talk you through every single question step by step. I might not mention every single method you could tackle the question using, just for the sake of time, but let me know in the comments if you'd like me to clarify anything which I've not done in this video. So without further ado, let's start together with question number 1. So question number 1, in an arithmetic series, the first term is 16 and the 21st term is 24. We need to find the common difference of the series. So we need to remember a couple of different formulae for an arithmetic series. I'll show you what they are here. In fact, one of them, is in the formula book, but ideally you should know them anyway. Here they are. So the term number is the first term plus n minus 1 multiplied by the difference between the terms, the common difference. This one you're not given. This one, I think it's fair to say, is fairly easy to remember with a tiny bit of effort. This one you are given. This is just from the formula book. So we can use these two formulae to work out what the common difference is and then answer part B. So the first term's 16. So in other words, A equals 16. So we may as well write that down in a moment. And the 21st term is 24. That means when n is 21, t subscript n is 24. So if we infill these two pieces, well, these three pieces, I suppose, of information into this formula, we can then work out what the common difference is. So 24, which is the 21st term, equals A, 16, plus n minus 1 multiplied by the common difference. So let's rearrange this and solve for d. So if we subtract 16 from both sides, we get that 8 equals 20d. Then obviously if we just divide both sides by 20, we can see that d equals a over 20, which simplifies to 4 over 10. And if you want to, you can call it as a decimal. So d is 4 over 10, or you can say it's equal to 0.4. For part B, we now need to find the sum of the first 500 terms of the series. Now here we're going to use the second formula, in particular this second equivalence here. And not the first one, because we don't know the last term. But we do know there's 500 terms to sum, and we know the first term is 16, and the common difference we worked out from part A is, from part A, that's 0.4. So again, if we just substitute into this formula, so for some of the first 500 terms, you're using this one here. So S subscript 500 will be a half times n, which means a half times 500. 2 lots of the first term, so 2 lots of 16, plus n minus 1, so 500 minus 1, multiplied by 0.4. You could do this on your calculator exactly as it already looks. Alternatively, if you wanted to slightly simplify it, you could do a half of 500 is 250, 2 lots of 16 is 32, and 500 minus 1 is 499. So if you wanted to, you could use this version and type this in on your calculator because it's slightly easier. You're less likely to make a calculator error. But anyway, taking your time and pressing the numbers in carefully, you should arrive at the figure of 57,900. So the sum of the first 500 terms is 57,900. Question 2, we have two functions f and g defined as follows. So f of x is 7 minus 2x squared, where x is any real number, and g of x is a quotient. G of x is 3x all over 5x minus 1, where again x is any real number, but this time x is not allowed to equal 1/5, because otherwise if it could equal 1/5, this denominator would equal 0, which we can't allow. Anyhow, we'll come to g of x later. First of all, what we need to do is to state the range of f. The range of f just essentially means what values of y it can take. So what's the maximum y, what's the minimum y? The range is all of it in between. So we're obviously minusing off something squared from 7. Something squared is always non-negative. So in other words, if we're taking away something squared, this value 7 can only get smaller than what it's starting off to be. So in other words, f of x is never going to be higher than 7, but can only be lower. That said, because x can be any real number, and 0 is a real number, if x were equal to 0, f of x can actually be equal to 7. So f of x essentially is less than 7 inclusive. So the first one, f of x is equal to 7 or less. Part B, we're asked to find gf of 1.8. So what this means is we need to find g of whatever f of 1.8 is. So you need to work out f of 1.8 first, and then substitute that into the function g. So f of 1.8, we just plug in place of x, the value 1.8. So f of x is 7 minus 2 lots of x squared. So if f is 1.8, that becomes 7 minus 2 lots of 1.8 squared. Try that on your calculator. You should get 0.52. So therefore, g of f of 1.8 means essentially g of 0.52, because f of 1.8 is 0.52. So we've got this function g, so g of whatever is 3 times whatever divided by 5 lots of whatever minus 1. If our whatever is 0.52, then g of 0.52 would be 3 times 0.52 divided by 5 times 0.52 minus 1, like so. So gf of 1.8, when we substitute it into the actual formula, becomes this. The final thing is just to actually type it in on your calculator to get the actual numerical answer, and you should find it comes to 0.975. Finally, for part C, we've got to find the inverse function g minus 1 of x. It's really important that you don't forget about the notation. This does not mean 1 over g of x. G to the minus 1 is how you write the inverse function. So what we're going to do here, we're going to write g of x in terms of y and x. So we're going to call g of x y and just leave x as it is. And afterwards we're going to switch the letters over. I'll explain as we're going. So first of all, write g of x as y, then say it's y equals 3x all over 5x minus 1. So if we do that as our first step, just rewriting g of x as y, we're going to make x the subject. That's the goal here. So we need to make x a subject. So what we need to do first of all is to multiply both sides by this denominator, 5x minus 1. If we do that, we get y lots of 5x minus 1 equals 3x. If we now expand these brackets, we'll get 5xy minus y equals 3x. To make x a subject, we want all instances of x together on the same side of the equation. So the suggestion here will be to subtract 3x from both sides, so that all the x's become on the left-hand side. That will then give us 5xy minus y minus 3x equals 0. So we want all the x stuff together and all the non-x stuff on the other side together. This y's got nothing to do with x, nothing to do with the subject which we're trying to find, so get rid of a y and put that to the other side. To undo minus y, we need to add y. So if we add y to both sides, our next step is 5xy minus 3x equals y. I've got two groups, but each group has an instance of x in it. So I can now get just one instance of x from these two by factorising out the x. So the next step, if I now factorise on the left, I'm going to get x brackets 5y minus 3 equals y. Finally, well, almost finally, getting x on its own, I can divide both sides by 5y minus 3. And if I do that, I get that x equals y all over 5y minus 3. I said it's almost the last step because, like I said earlier, we need to switch these letters around. So once I've got x as a subject, the final step now is just to re-letter x and y. So now what we're going to do, essentially, is just relabel. We're going to relabel x now as g minus 1 of x, and relabel y here as x. So essentially we've got g minus 1 of x equals x all over 5x minus 3, after we relabel it to pick up full marks so it makes algebraic sense. Question 3, using the laws of logarithms, solve the equation log base 3 12y plus 5 minus log base 3 of 1 minus 3y equals 2. The first thing you might want to notice is a lack of consistency within this equation. On the left-hand side, we have it in terms of log base 3, and on the right hand side we don't. But that's easy to fix because log base 3 and 2, because 2 is a fairly, well, 2 is a very small number, we can actually work out what this would be in terms of log base 3. So what we need to ask ourselves is, what power of 3, basically what power of 3 is 3 squared? Or 3 squared, of course, is 9. So what we can say here is this 2 can be replaced with 9, because 3 squared, the base of the logarithm to that value is 9. So this can be replaced with log base 3 of 9. So now I've got that step complete, we can now look at the left and simplify this using laws of logarithms. So it's good of the examiner to give us almost a little clue here, really. So we've got log of one thing minus log of another thing, and the logs are to the same base. So log A minus log B, as a general rule, is log of A divided by B. So I can combine these two into a single logarithm. This becomes log base 3 of 12y plus 5 divided by 1 minus 3y, like so. So now, obviously one side's equal to the other. Not only that, but both things are two logarithms to the same base. So because this is log base 3 of something, and this is log base 3 of something, and both sides are equal. If the bases are equal, and both sides of the equation are equal, then what we're actually taking the log of must also be equal. So because log of one thing equals log of the other, then essentially what we're logging must be equal to one another as well. So essentially, all we can say here is this thing in the brackets must equal 9. So now we can go from something which is a log equation to something which is much simpler, after manipulating it into something we can see what to do, of course, using the laws of logs. So now we need to solve for y. So this is going back to GCSE now. Now we've done the A level step. It's unravelling, going back to basics. So if we multiply both sides of this by 1 minus 3y, we'll get 12y plus 5 equals 9 lots of 1 minus 3y. If we now expand this right-hand side, we get 12y plus 5 equals 9 minus 27y. I could now add 27y to get all the y's onto one side. That'll now give me 39y plus 5 equals 9. If I now subtract 5, I can see that 39y must equal just 4. Then as my final step, if I divide both sides by 39, therefore y must equal 4 39ths. Question 4. Given that theta is small and measured in radians, use the small angle approximations to show that 4 sine theta over 2 plus 3 cosine squared theta is approximately equal to a plus b theta plus c theta squared, where a, b and c are some constants we need to find. So using small angle approximations. The good news is, as long as you remember it's given to you, it is given to you. So as long as you remember it's given, get your formula book out if you need to, and refresh your mind. Here they are. So if it's measured in radians, which is key, doesn't work in degrees. If theta or the angle's in radians and it's small, typically thinking about 0.1 radians or less in terms of what a small angle is, very roughly speaking. Sine theta approximates to theta, cos theta approximates to 1 minus theta squared over 2, and again tan theta approximates to theta. So it's easy to not make the mistake as such, but to go down maybe a slightly more awkward route by thinking, oh, I've got sine theta and cos thetas, so I'll use this one and that one. But actually, if you just have a little think about it, on the right-hand side, the highest power we're wanting to go up to is something in terms of theta squared. Now, if I use this one for cos theta, which has a theta squared term in it, and then take cos theta and then square that again, I'll end up with something to the order of theta to the power 4, because this thing here will get squared if I take the cos squared of it. So what I can do to get round that, I can get it all in terms of sine thetas, or sine theta over 2's. So I can replace cos squared theta with 1 minus sine squared theta. Therefore, my answer will then be all in terms of theta rather than being something else. So if I do this now, just using this one here, I get the following result. So just replacing the cos squared theta with 1 minus sine squared theta. But if I just make this more explicit and just say that 1 minus sine squared theta is the same as 1 minus sine theta in brackets all squared. Just to make it really explicit, what I'm doing here is I'm saying it's going to be 4 sine theta over 2 plus 3, then it's going to be 1 minus theta squared. It's going to be approximately equal to that. So up to this point you can use equal signs because cos squared is identical to 1 minus sine squared theta, and sine theta all squared is how sine squared theta is defined. It's now you can use the approximately equal to's, because it's at this point here we can say that sine theta over 2 approximates to theta over 2, thinking of theta over 2 as a different version of theta. Call theta over 2 equals x if you like. So sine of an x becomes an x. This one here, again because theta is small, sine theta goes towards theta, and so sine theta squared tends towards theta squared. If you now expand this out, 4 lots of half theta becomes 2 theta, 3 times 1 becomes 3, and 3 times minus theta squared, of course, is just minus 3 theta squared. We could probably get away with leaving our answer like that, but because it says to give it in terms of ascending powers of theta, so the constant theta, then theta squared, if we just take an extra little step just to show willing and reorder it into this form, we can see that this expression here is approximately equal to 3 plus 2 theta minus 3 theta squared. Not that you need to, but essentially you could say that therefore A is 3, B is 2, and C is negative 3. For question 5, we have a curve C with equation y equals 5x to the power 4 minus 24x cubed plus 24x squared minus 32x plus 11, where x is any real number. Part A is very, very generous. I mean, really 1 mark each, I think, but you know, still generous. It's just algebraic differentiation. So just bringing the powers to the front and multiplying the coefficients by the powers. Then obviously drop the powers down by 1. So this first one, for example, the 4 comes to the front, multiplies for 5. So we're going to have 5 times 4, 20, and 4 becomes 3. So 20x cubed. This one here, the 3 will come to the front and multiply the 24 to give 72, and then 1 less than 3 is 2, so we get then minus 72x squared. This one will become plus 84x. Minus 32x will just become minus 32, and the constant will just disappear. So dy by dx becomes this, and going 1 step further in the same way, d squared y over dx squared just means to differentiate dy by dx again. That's going to give us 60x squared minus 144x plus 84. Part B, part 1, verify that C has a stationary point when x equals 1. Well, if there is a stationary point at x equals 1, all that means is that the gradient is flat there. In other words, the gradient is 0. So because we've got the gradient function from A part 1, we can substitute in what the gradient actually is when x is equal to 1. So if we do that now, dy by dx when x is equal to 1 will be 20 multiplied by 1 to the power 4 minus 72 times 1 squared, just substituting in 1 in place of x because x is equal to 1. And if you work this out on your calculator, you'll get an answer of 0. So that has verified that C has a stationary point at x equals 1. So you might want to conclude just by saying that. It can't hurt to do so. B part 2. Now we need to show that the stationary point is a point of inflection, given reasons for your answer. To find if it's a point of inflection or not, this is why we need to use d squared y over dx squared. So again, the setup of this question is actually quite benign. It's giving you clues here that dy by dx might be useful in part B, and that d squared y by dx squared might have a use in part 2. And indeed it does. So, like we did with B part 1, where we try x equals 1 in the function dy by dx, if we now evaluate d squared y over dx squared, the second derivative when x is equal to 1, and so what that gives us 0 as well. And so because the first derivative, dy by dx is equal to 0, and the second derivative is equal to 0, then what we need to do to establish what sort of stationary point it is, we need to test the second derivative either side of x equals 1. So we're just talking just a tiny change either side. Plus or minus 1 decimal place I think is normally sufficient. So if I just go for 1 minus 0.1 and evaluate d squared y over dx squared when x is 0.9. So when x is 0.9, d squared y over dx squared is 60 lots of 0.9 squared minus 144 lots of 0.9 plus 84, which equals 3. Importantly, that's greater than 0. If I now go 0.1 higher than 1 and try what the second derivative is when x is equal to 1.1, I'll get the following. I get a value here now of negative 1.8, and importantly now that's less than 0. If you're thinking, well, did I need to go 0.9 and 1.1? What if I tried a 0.8 and 1.2? Well, that's fine as well. Okay, so as long as you're not going like 0.6 or 0.7 away, you're okay. So 0.1 or 0.2, I'd probably say no more than that, but as long as you just point a few decimal places, no more than that either side, marks are rewarded. So what we've seen here is the second derivative at x equals 1 is equal to 0, but there's a change of sign in the value of the second derivative before the stationary point and after the stationary point. So these two things combined are proof that it's a point of inflection. So just to really confirm and establish you'll get the marks, if you're confident, I'd also suggest to add a bit of wording in as follows, something like this. So since dy by dx and d squared y over dx squared are both 0 when x is equal to 1, and d squared y over dx squared changes sign either side of x equals 1, then x equals 1 is a point of inflection. So I've got this weird shape here for question 6. So the shape itself has got a weird enough name to say. So the shape OABCDEFO, shown in figure 1, is a design for a logo. So in this particular design, OAB is a sector of a circle, centre O, radius R. Sector OFE is congruent to sector OAB. So in plain English, it's just saying that this sector here and that sector here are exactly the same size, same shape, same area. So that essentially is a reflection of that one. So there's going to be a line of symmetry down the middle. That's one way you can think about it to begin with. AOF is a straight line. So A to O to F is a straight line. Angles on a straight line, of course, add up to 180 degrees, going back to GCSE. That's an angle fact we're going to be using in just a moment. And I almost missed off that ODC is a sector of a circle, centre O, radius 2R. So O to D to C is the bigger sector. And in fact, the radius of the bigger sector is double the radius of these two smaller sectors. From the centre to F, or from the centre to A, these two little ones have just got a radius of little r. But this bigger sector at the middle, from 0 to D, has got radius 2r. So this radius is double as long. So given that the size of angle COD is theta radians, so we're measuring in radians now, not degrees, write down in terms of theta the size of angle AOB. So AOB is just this angle here in the middle. So there's nothing to go off apart from the fact that it did say that AOF is a straight line. So if this is a straight line, then from here to here, all the way around would be 180 degrees, which in terms of radians, 180 degrees, or half a turn, is pi. And so, in terms of these two missing bits, which we don't know, we know this is theta, we know all of this is pi, then these two bits combined will be pi minus theta. And because these two sectors are congruent, if the two remaining ones here sum to pi minus theta, then we share that equally between each of them. So each angle is going to be pi minus theta all over 2. So what I'm going to do now, it can't hurt to get that labelled in on the diagram. So each one here is going to have an angle of pi minus theta all over 2. Part D, we have to show that the area of the entire logo is half r squared brackets 3 theta plus pi. So this entire logo we can think of as being a sum of 3 different sections. There's 2 smaller arcs which are equal in area, here and here, and one much bigger arc in the middle. So if I just colour code these in red and blue, these 2 red ones, the smaller ones, are one and the same, because like the question says, OAB and OFE are congruent to each other, and this one obviously the radius is double. We need to remember in terms of radians that the area of a sector is a half r squared theta. So if we add up the sum of these 3 different sector areas, we're going to get this result here. So the area of the logo is of course the area of the small sector plus the other small sector, plus the area of OCD, the larger sector, and we're going to get this result. So, explaining where this comes from, the general formula for the area of a sector is half r squared theta, where r is the radius of the sector and theta is the particular angle you're talking about at the centre. And so this one here, well, these two have radius r, hence the half r squared, and the angle at the middle, the angle subtended in the middle, if you want to be fancy, is pi minus theta over 2. So half radius squared times angle at the middle. Exactly the same for the other one, because that one's congruent. Half times radius squared times angle at the middle. And for this one here, half times radius squared, because this radius is 2r, that means half times 2r all squared multiplied by the angle at the middle, which is just simply theta. So if we take this and try and make it slightly simpler, because this doesn't look very simple at all at the minute, I've got a half r squared something plus another half r squared something. A half r squared plus another half r squared will become a full r squared. So I can simplify this into r squared brackets pi minus theta over 2 plus a half 2r all squared theta. In fact, I can go one step further and simplify it into this. So these 2 red bits become this, like I say, and then a half times 2 squared is a half times 4. That becomes 2. So I'm going to get 2 r squared theta. If I now expand this out, I'm going to get 2 fractional bits. So I've got pi over 2 times r squared. So in other words, that's half pi r squared. Then I get minus a half theta times r squared. So expanding it out, I get this result. And then I'm pretty much done, because we can see now that the half is going to be a common factor, as is r squared. I've got r squared in each term here. Theta r squared is the same as r squared theta. So 2r squared minus a half of r squared theta, that overall will be 1.5 r squared thetas. And 1.5 r squared thetas is the same as 3 halves. Hence the 3 halves r squared theta part there. And then of course we'll just have half pi r squared. So when you factorise out the half r squared, you get the pi there. So we're so close to being done, we can just write the final step in. So I've been so clear with doing this, we've earned the right to just say, that then would simplify to being a half r squared brackets 3 theta plus pi, if you were to factorise it. Part C, find the perimeter of logo, giving your answer in simplest form in terms of r, theta and pi. So the perimeter, now I'm going to label in two different ways. I'm going to label it in terms of the straight edges and the curved sections of the circumferences, the arcs. So I'm going to label these in terms of yellow bits and green bits. So yellow is going to be the straight edges, green the arcs. So if we just think about the straight edges, the perimeter is all the way around the outside, so we're going to have 4 straight edges in my mind. Well, suppose you can think of this as just 1 straight edge, 2 and 3. In fact, fair enough, it is 3 straight edges. And then also 3 arcs, 1, 2 and 3. But in terms of the straight edges first, this bit's R and that bit's R, so that's a total of 2R. It's tempting to think, well, this bit's 2R as well, because it says 2R. However, the 2R means all the way from O up to C. We know that from O to B is R, so if that's R, this must be the extra R. So this is just a single R, by symmetry that's also R. So R plus 2 R's, we're going to have 4 R's in terms of the straight edges. I'll now explain about the green bits here. We need to remember as well, in the same way that the sector area in terms of radians is half r squared theta, we need to remember the formula for arc length. Arc length is r multiplied by the angle at the middle. So for these two smaller ones here, arc AB and arc EF, this one and this one, the radius of each arc is r, and the angle at the middle that it makes is pi minus theta all over 2. So r times angle at the middle for the first sector, then plus r times angle at the middle for the second sector on the other side, and then for the bigger sector, r times angle at the middle. This radius is 2r, angle at the middle is theta, hence the 2r theta. So again, in a similar way to before, we can simplify this so we get our answer in simplest form. This isn't simple yet, although you would get some credit for this, not full credit yet. So these fractions here, we're going to get half pi times r plus half pi times r. So half pi times r plus another half pi times r, we're going to get pi r. And in the same way, we're going to get minus r theta divided by 2, and another minus r theta divided by 2 here. So that's going to give us overall a full minus r theta. So if we expand this out and slightly simplify, the next step would be 4r, we can leave as 4r. This bit expanded out along with the other one and give us pi r, like I said. Then minus theta r, then 2r theta, we can just leave as 2r theta. This is almost as simple as it goes, but theta r is the same as an r theta. So 2r theta take away what essentially is an r theta would leave us with just 1 r theta. So finally, this becomes 4r plus pi r plus just 1 r theta, like so. For question 7, we're told quite clearly to show all stages of working, and solutions relying entirely on calculator technology are not acceptable. So using numerical integration or algebraic integration on a calculator without showing a method is only going to be useful as a checking procedure. You're not going to get any method marks or any credit for just using that. So we need to show really clearly what we're doing here. Part A, well, I should have explained really about the question, to be fair. We've got a curve C with this cubic equation, x cubed minus 10x squared plus 27x minus 23. The point P, 5 minus 13, lies on C as such, and L is a tangent to C at this point P. So for part A, we need to use differentiation to find the equation of L, given the answer in the form y equals mx plus c, good old GCSE form, where m and c are integers to be found. So it says use differentiation, so clearly what we need to do is, if we're to find the equation of L, if L's a tangent, we need to find the derivative of c and then substitute in the x value of c at the actual point we want to find the gradient of a tangent at. So first of all, if we find dy by dx by differentiating this, we've got 3x squared minus 20x plus 27. So now, of course, we want to work out what this is. This is a gradient function, and we want to work out what the gradient would be at this point here, at the tangent. So we want to sub when x is equal to 5. So if we substitute in to this quadratic, x is equal to 5, we can see that the gradient, when x equals 5, in other words, the gradient of the tangent, is going to be 3 times 5 squared minus 20 times 5 plus 27. And if you work this out, it gives you actually exactly 2. So the gradient of a tangent at the point x equals 5 is a gradient of 2. So in terms of how to write down the equation of this tangent, because a tangent's a straight line, and we need to give it in this form y equals mx plus c, we've now at least worked out the gradient part. We've worked out what m is. M is 2. So now y equals 2x plus c, where c is some y-axis intercept we need to work out. But we can work out that now because we know a point that the tangent goes through, because the tangent goes through point P. So if we substitute into this, x is 5 when y is minus 13, then we're going to get the equation minus 13 equals 2 lots of 5 plus c. 2 lots of 5, of course, is 10. So negative 13 equals 10 plus c. If I just subtracted 10 from both sides, it should be fairly obvious to you to see that the value of c is negative 23. So if we want to find the equation of this tangent in the form y equals mx plus c, well, we found m is 2, and we found c is negative 23. Essentially, we have our answer. The only thing we need to do is just to write it down. So therefore, in the form y equals mx plus c, our tangent is y equals 2x minus 23. Part B, I'll admit, did confuse me for a minute when I read it. It's actually very obvious when you just take a step back and think about it from afar. Don't think about this too deeply. It says, hence verify that L meets C again on the y-axis. So you might be tempted to think, well, do I put one equal to the other and see where they meet, and then verify that they meet when x is equal to 0? Again, it'd be overcooking it, really. The easier thing to do is just to realise and remember, really, because on some level you will know that when we cross the y-axis, the value of x is 0. So it's quite clear to see. If we were to substitute into both equations, x being equal to 0, then for curve C's y-intercept would be nothing, 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 minus 23 here. And the tangent's intercept, again, sub when x is equal to 0, y would be again equal to negative 23. And it even tells us on the graph. Okay, so it's telling us in a way, so it's almost too obvious. But in terms of how to explain it using the algebra and using the maths we have, I would say that if x were equal to 0, for both equations, we'd get that y is equal to minus 23. So something like this would suffice. So L and C would meet when x equals 0. Both L and C pass through 0 minus 23. Thus, they meet again on the y-axis. This is another way of saying they do meet on the y-axis because this is a shared y-axis intercept. Finally, part C, the finite region R is bounded by the curve C and the line L. So use algebraic integration to find the exact area of R. There's a few different ways of doing this, and different teachers may explain it in different ways. And again, if you were to search out a different video, no doubt a different video would explain it a different way. A common way of doing this is to consider this as being the area trapped in between the x-axis, a curve, and a straight line. So what we could do there would be to take the integral from this point and that point for x of the curve, then minus the integral of the line. I would rather always think of this in terms of geometry. This is just my own preference. I'm not saying it's better or worse. But in terms of finding this area R, let's just think about this in terms of pieces on the graph. So if I just add a vertical line from P going upwards to the x-axis, just to enclose this region R, and then also as well, remembering that when I take the integral and a curve is underneath the x-axis, if I were to integrate a curve which is underneath the x-axis, in between x being, for example, I don't know, 0 and maybe this is 5, what that tells us is the area in between the curve and the x-axis. So when we integrate it, what that would tell us is this white area down here, this tiny sliver, and all of this. So if I were to integrate this function between x being here and here, I'd find out this area. I'm going to colour it in pink. But of course we don't want to find the pink area, we want to find this region R. I'll come to that in just a moment. If I just think about what I've created here, this is actually a trapezium. So if I add on a bit more information about this trapezium, if I call this point A and that point B, this is just the y-axis intercept, which part B tells us really is 0, minus 23. And this point here is just the same x-coordinate as P below it because this is a vertical line. So because this is on the x-axis, this is going to be 5, 0. So in terms of the dimensions of this trapezium, from here to here, well, that's going to be a length of 5. And from here down to minus 23, obviously it's a distance I've gone down of 23. So this length would be 5, and the distance here would be 23. In the same way, if that's 0 for y and this is minus 13, the change in the y direction is 13. So from that we could work out the area of this trapezium. And as I've said, this pink area is given to us by taking the integral of the curve in between 0 and 5. So what we need to consider now is finding the pink region P. So like I've said, the area of the pink region would be the integral from 5 to 0 of this function C. So this is fairly simple to integrate. We're just going to add 1 to the power and divide by the new powers. So this is going to give us this result. X cubed becomes a quarter x to the 4. Minus 10x squared becomes minus 10 over 3x cubed. 27x would integrate to the expression 27 over 2x squared. And minus 23 would integrate to minus 23x. So I now need to just input the upper limit of 5, and then if I really wanted to, then input the lower limit of 0 and subtract it away. But hopefully you can see, if I were to input x being 0 into all of these terms, that would just give me 0 for everything, and so there's no real point in putting in the lower limit because it's going to be absolutely 0 anyway. So substituting in 5 for x gives us this. So the area of P, we're going to have a quarter, 5 to the power 4, minus 10 over 3, 5 to the power cubed, plus 27 over 2, 5 squared, minus 23 times 5. And that should give you an area of minus 455 over 12. Well, why would an area ever be negative? Well, this is why I always consider it in terms of pieces, and also in terms of what I've just done algebraically and geometrically. I've integrated a curve underneath the x-axis, and so there's no intersection with the x-axis, and so all of this curve on the interval from 0 to 5 is all underneath. And what happens is, if you integrate to find the area of a curve, but the curve itself is entirely underneath the x-axis, the integral will always come out to be negative. And what we do to make sense of this is, if we're evaluating an area, then the area is just simply the modulus. It's the absolute size of this. So the area is just the modulus of minus 455 over 12. In other words, the area is just this without the minus sign there. So the area of the pink region, area of pink P, is 455 all over 12. if I now consider this whole shape from O to A to P to B, O, A, P, B, this trapezium shape, then because I know the dimensions of it, I know the two parallel sides are 23 and 13, and the distance between the parallel sides is 5, so I can calculate the area of the whole trapezium, and I know this pink region. Therefore, I can calculate this shaded region R. I can find what I want by working out the area of the whole trapezium, and then subtracting from that the pink area P, 455 over 12, which we've just found. So in other words, as an equation, area R will be the area of a whole trapezium minus area P. So area of trapezium is basically, I always think of it as the average length of the two parallel sides. So 23 plus 13, add those together and divide by 2. So a half of the sum of the two parallel sides multiplied by 5. So that's a whole trapezium, then minus off the pink region, 455 over 12. That'll tell us area R. And so if we were to do this now on a calculator, so if I just do this here, so I'd have 1/2, whoops, help if I could actually type the numbers, 1/2, 23 plus 13, close brackets, multiplied by 5, then minus off the fraction 455 over 12, I get a value of 625 over 12. So in other words, the exact area as an exact fraction is 625 over 12. Question 8, we have a curve, capital C, with equation px cubed plus qxy plus 3y squared equals 26, where p and q are constants. For part A of this question, we need to show that dy by dx is apx squared plus bqy all over qx plus cy, where a, b and c are integers to be found. So obviously it's a case of having to differentiate this because we need to show that the derivative of it is this. So the question's telling us what to do, but this isn't a standard thing to take the derivative of, because this is a function of x and y. This is also a product of two different things. This is something you can think of as being qx multiplied by y. So this will be the product rule for differentiation and also implicit differentiation. And to differentiate 3y squared, again, will be a case of differentiating something implicitly. So I'll talk you through step by step, finding dy by dx of all of this. So first of all, let's just write it down. So px cubed plus qxy plus 3y squared equals 26. Well, px cubed, that's really easy to differentiate. That 3 just comes to the front, multiplies a p, and then that power of 3 becomes power 2. So if we find the derivative of both sides, as I say, starting with the px cubed, that'll just become 3px squared. Next in blue, let's think of this as a product, qx multiplied by y. So to differentiate a product, the first thing is to hold constant the first term and then multiply it by the derivative of the second term. So if I hold qx constant and multiply that by the derivative of the second term y, the first part of this will give me qx, and that becomes dy by dx. So you get qx dy by dx. Then the second part of the product rule is I then also add on to that the derivative of the first function multiplied by the second function held constant. So now I'm going to differentiate qx with respect to x and hold the y constant. So qx will differentiate to q, y stays as y, so I'll also get a plus qy here. That's a mixture of implicit differentiation with a dy by dx and also the product rule for differentiation. 3y squared, this is a case of implicit differentiation. If it's just a case of a function of y or y squared, the way I'd imagine this is to imagine it being a function of x. So just pretend it's 3x squared and differentiate it as normal. So if it were 3x squared, that would differentiate to 6x. If we're differentiating 3y squared, we treat it in exactly the same way, but the trick is to just stick a dy by dx on the end. So because 3x squared differentiates to 6x, 3y squared will differentiate to 6y with a dy by dx stuck on the end. And then if we differentiate the right hand side, quite obviously, the 26, because it's a constant, will just differentiate to 0. So that arguably is probably the most difficult step to show. It is a show that question, so we need to show that this differentiates to this in the first instance. Now what we can do is just neaten this up. So if we subtract 3px squared and subtract qy, so we just leave anything to do with dy by dx on its own, so we can factorise that out on the next step, we'll now have qx dy by dx plus 6y lots of dy by dx equals, on the right hand side, minus 3px squared minus qy. We can now factorise on the left hand side. So if I factorise out the dy by dx, this now becomes dy by dx, then in brackets qx plus 6y, and the right hand side stays the same, just minus 3px squared minus qy. Finally, to get dy by dx on its own, and show this to be true, I'll just divide everything by this bracket. So if I divide both sides now by qx plus 6y, the final result is therefore dy by dx is minus 3px squared minus qy, all divided by qx plus 6y. So by showing the steps carefully and methodically, we've shown it fully, that's full marks. Part B, now going to be using part A to do this part B. So we're told now the point capital P, where x is minus 1 and y is minus 4, lies on C. And the normal to C at P has equation 19x plus 26y plus 123 equals 0. Find the value of P and the value of Q. So it's one question, but we need to find two things. So either, case 1, we can find two different equations, where one equation's in terms of just one variable, get an answer, and we get a second equation, which is just purely in terms of the second variable, and get an answer for that one. The second scenario, which is actually more likely for A level, is we're going to have two unknowns, and we're going to have two equations involving these two unknowns, and then we might have to solve something simultaneously. So just bear in mind, because we're trying to find two things, we might need to find two equations. So the first thing is to notice that we're told a point that lies on C. So we can substitute in a value of x and a value of y into this to get a simplified equation relating P and Q together. So if I do that as a first step, if I sub minus 1 and minus 4 into this equation here, I'm going to get P multiplied by minus 1 all cubed plus Q multiplied by minus 1 times minus 4 plus 3 lots of y squared, so plus 3 lots of minus 4 squared equals 26. This will obviously simplify. Minus 1 cubed is just minus 1, so I get minus P. Minus times a minus is a plus, so I get minus 4Q. And 3 times minus 4 squared, again, square something becomes positive. 3 times 16 is 48. If I then subtract 48 from both sides, I've then got my first equation in terms of P and Q. So essentially, I can see that minus P plus 4Q must equal minus 22. The second bullet point is a second piece of information. It's about the normal to C. So the normal to C at this point P has equation 19x plus 26y plus 123 equals 0. So I could work out the gradient of a normal, and I've got an expression here for dy by dx. I've differentiated the function. That tells me the gradient of a tangent. So gradient of a normal I can work out from this one, and then I can relate that to the gradient of a tangent later. So the first step, let's take this equation for the normal, and then step by step get it in the form y equals mx plus c, so we can deduce the gradient of it. So if we now subtract 19x and subtract 123 from both sides, we'll now get it into the form 26y equals minus 19x minus 123. Then if we divide everything by 26, we now can see in the form y equals mx plus c that the normal has equation y equals minus 19 over 26 x minus 123 over 26. So, quite clearly, that means that the gradient of a normal is minus 19 over 26. I'm running out of space, I'm just going to pop this over here now. So, the gradient of a normal, minus 19 over 26. However, what we could really do with knowing is the gradient of a tangent. dy by dx is the gradient function which tells us the gradient of a tangent. The gradient of a normal is always perpendicular to the gradient of a tangent and vice versa. The normal and tangent are perpendicular to one another, so therefore we should remember that the gradient of one will be the negative reciprocal of the gradient of the other. So therefore the gradient of a tangent will be the negative reciprocal of minus 19 over 26. So the minus switches to a positive, and the 19 goes to the bottom, 26 goes to the top. So the gradient of a tangent at point P is 26 over 19. But now, because I know what the gradient is numerically, and I know what it is in terms of P and Q, I can now get a second equation relating P and Q together, which can then afterwards simultaneously solve with this equation I already have in this pink rectangle. So, therefore, the gradient at point P, where x is minus 1 and y is minus 4, is this expression here, with x subbed in minus 1 instead, and for y, we sub in minus 4. So this will simplify somewhat, and of course, the gradient at point P, we now know is 26 over 19. So I can say 26 over 19, this bit becomes minus 3p, minus q times minus 4, so it becomes positive 4q, and q times minus 1 is minus q, and 6 times minus 4 is minus 24. We've got a fractional equation to solve. There's a few ways of doing this. My personal preference is to cross multiply. So if I multiply this numerator by the denominator, and this denominator by that numerator, I'll get this line now. And I get that minus 26q minus 624 equals minus 57p plus 76q. If I now get this into a similar equation to this one, where I have p and q on one side and the number on its own on the right, I could add 624 to both sides, and then add 57p to both sides, and then subtract 76q to both sides. Because I'm trying to be a bit efficient with space, I'm skipping a few of those steps, but I'm hoping you can convince yourselves that from here, we can go to this step here. Convince yourselves that this would simplify into this equation. So now I've got the second equation of 2, so I can solve them simultaneously. Just to make it easy, I'm going to put this one next to the second one, because almost always with simultaneous equations, you want them next to each other when you're going to solve them. So now, all we need to do is, as I say, solve these simultaneously. So I'll show you how to do this on a calculator. Different calculators do it in different ways, but essentially with a decent enough scientific calculator, I'd be very much surprised if there isn't a similar function to what I'm going to show you to solve a linear simultaneous equation pair, as I'm going to show you right now. So on this one, if I go to menu and scroll to option A for equation / function, press equals, press 1 for simultaneous equation. Number of unknowns is 2, just p and q in our case. Now it gives it in terms of x's and y's. This doesn't matter, it's entirely arbitrary as long as we're consistent. My suggestion is we think of the x here as being p and think of the y as being q. So the first line is minus p, so that's minus 1 in terms of x. So if I type in minus 1, minus 1x, minus 1p. Then plus 4q, so I put the 4 for the second variable, and that equals minus 22. The next one, 57p, so type in 57x, minus 102q, so type in minus 102 for y, and that equals 624. And press equals again. We get that x is 2 and y is minus 5. But in our case, x corresponded to p and y corresponded to q. So in other words, p is 2 and q is negative 5. So therefore our final answer, like I've shown you on the calculator, or you could do it manually of course if you want to, p is 2 and q is negative 5. Question 9 is the sum of a series, the sum to infinity in fact. So we're asked for the sum to infinity. The first piece of good news is, as long as you remember this is in the formula book, great, so that's a piece of help. So first of all though, it's a product and you've got an awkward power and this just looks evil. So what I would suggest in these cases is just to manually work out what the first several terms are, and almost always you will spot some form of pattern. Remember, the examiner can only ask you really about an arithmetic sequence where you can normally see what each term is increasing by, just by working out manually. Or if it's geometric, you can see what's happening from one term to another, what it's been multiplied by. So if we just manually work out, for example, when n is 2, n is 3, n is 4, and so on, just by switching in some values, we'll see what's going on behind the scenes. So when n is 2, we're going to get 3/4 squared multiplied by cos of 180 times 2. If you try that on your calculator, you'd get 9 over 16. So essentially you get 3/4 all squared, which is 9 over 16. And cos of 360, well, cos of 360 is the same as cos of 0, and cos of 0 is 1. So it's just knowing the period of cosine, really. But if you don't, just manually on your calculator, when n is 2, you get 9 over 16. Now let's try when n is 3. When n is 3, the third term will be 3 over 4 cubed. So the second term, I should really say, because we're starting from when n is 2. The second term will be 3/4 cubed multiplied by cos of 540. That would give minus 27 over 64. When n is 4, we'll get 3/4 to power 4 multiplied by cos 720, which is 81 over 256. And when n is 5, again we get this. So we can hopefully see a pattern. So for example, if I have a look at the top numbers, 9, 27, 81, 243, they're being multiplied by 3, and 16, 64, 256, the denominator is being multiplied by 4. So the common ratio is 3/4. Or so it would be if all these values were positive. They're not. They're oscillating between positive and negative. And that will only happen if the common ratio is a negative value. So by inspection, you can see that the common ratio is minus 3/4. Or what I'd suggest you probably want to do to be safe and to do it using a calculator is just take one value and divide it by the previous one. So if I were to take, for example, let's go back to normal mode on my calculator. The easy ones would be the first couple, of course. So if I were to take minus 27 over 64, I'll type that in as an equals, in fact, then divide that by 9 over 16, I get minus 3/4, which tells what the common ratio is. I could try it for a different one as well if I wanted, as long as it's consecutive terms. So 81 divided over 256, that divide by the previous term, which is, I'll put in brackets, negative 27 over 64. This again will give me a common ratio of minus 3/4. So as I say, either by inspection or by calculation, the common ratio is minus 3/4, and as well as that, the first term comes out to be 9 over 16. So therefore, the first 4 terms of this, of course, we've generated, and like I've just talked through, we can see that the first term is 9/16, this one here, and the common ratio is negative 3/4. Now this is in the formula book for sum to infinity is the first term divided by 1 minus a common ratio. So plugging in these values here for sum to infinity will be 9/16 all over 1 minus 3/4. I'll show you to do it on the calculator because sometimes with being awkward it can throw people off slightly. If you press fraction and then press fraction again to get a fraction within a fraction, that's absolutely fine. So 9/16, then 1 minus, press fraction, 3/4. We get 9/28. So the sum to infinity, as an exact fraction, is 9/28. Question 10 is talking about exponentials and logarithms. So the time in capital T seconds that a pendulum takes to complete one swing is modelled by the formula capital T equals AL to the power B, where L meters is the length of the pendulum and A and B are constants which we're going to need to find in a moment. So for part A we need to show that this relationship here can be written in the form log base 10 of T equals B log base 10 of L plus log base 10 of A. So we just need to take this here and then change it using the laws of powers and logarithms which we should have recapped and revised. So let's just start off with T equals AL to the power B. If we take logs of both sides of this equation, then taking logs has the power to, I shouldn't have used the word power really, it has the ability to bring the power to the front of a variable. So this power B will be brought to the front in a second. But the first step, if I take log base 10 of both sides, I'll get this. I'm going to get that log base 10 of T equals just log base 10 of the product of A, L, B. The first thing I'm going to do now is to split this, because log base 10 of A, L to the power B is a product of A and L to the power B. If I'm taking the log of a product of two things, that's the same thing as taking the log of one thing plus log of the other thing separately. So essentially I can partition this into two separate logarithms. So the next step, I'm just going to split this into two and call it log base 10 L to the power B plus log base 10 A. If you're wondering, well, why don't I put the A first and then the L to the power B last, the same as the order the letters appear here, it's because I'm trying to show that this relationship can be written in this form here. And in this form, L comes before A. That's why I've put the L before A here, whenever we ordered it. Now again, using the laws of logs, we need to remember that if you've got log to any base to some variable to any power, that's the same as having log to the same base to the same variable, with this power brought to the front and multiplying it. In other words, I can just shove this B to the front and just multiply it all by the log base 10 of L, and it's the same as this. So that's my final step, to go from this to that. So therefore, log base 10 of T equals B log base 10 of L plus log base 10 of A. Part B, a student, presumably in some physics lab, is now carrying out an experiment to find the values of the constants A and B. The student recorded the value of capital T for different values of L. Figure 3, this graph here, shows the linear relationship between log base 10 of L and log base 10 of capital T for the student's data. The straight line passes through the points minus 0.70 and 0.21, 0.45. These 2 points as labelled. So using this information, find a complete equation for the model in the form capital T equals AL to the power B, given the value of A and B each to 3 significant figures. So we've proven that this model will yield the linear relationship as shown in the graph. So we can then use the graph to work out these values here, and then reverse it to go back to what the original form was, once we know these variables. So it should be no surprise to us that this gives a straight line graph. The standard equation for any straight line, as you well know, is y equals mx plus c. Y is a variable, m is a constant, x varies, x goes along, y varies, y goes up and down, and c, the y-intercept, again is a constant. So the equation y equals mx plus c takes the form variable constant, variable, constant. This is the same thing here. Variable, b is a constant. Variable, because log base 10 of L varies, and that's going to be a constant too. If a is a constant, log base 10 of A will also be a constant. So, using this information, we can now piece together what these constants are. So the first thing, let's just start with the equation again. So log base 10 of t is essentially the y-axis. That's like our new y in inverted commas. X is like log base 10 of L. So that's our x. This is our y. And then to fit it in terms of y equals mx plus c, then this constant here, this log base 10 of a, must correspond to the y-axis intercept. So log base 10 of a will correspond to this point here. And of course, using the idea that this is y equals mx plus c, you can hopefully see that the m, the gradient, will relate to this constant b. So I can work out this constant b by working out the gradient of this straight line m, then that's one and the same as what b is. So how can I work out the gradient of a straight line? Well, obviously it's the change in y divided by the change in x. But in our case, we're not talking about y and x anymore. We're talking about log base 10 of t and log base 10 of L. So slightly adapting the standard idea of a gradient, our gradient here to find m, which is the same as b, I could have put b or m here, it doesn't matter because we're one and the same. It's changing y, if you like, which is log base 10 of t, divided by the change in the new x axis, log base 10 of L. We know 2 points on this line, so we can input these two values. So I know that y goes from 0 up to 0.45. I know that x goes from minus 0.7 up to 0.21. So I can work out the change in log base 10 of t and the change in log base 10 of L, like so. As an exact fraction, I'd get 45 over 91, but the question clearly says to give our answers for b and a to 3 significant figures. So we can just type in 45 over 91 on the calculator now, and so that gives us as a decimal. So 45 over 91, and press equals, and press S arrow D, we get a decimal answer of 0.4945 and so on and so on. So to 3 significant figures, that'll round to 0.495, because next to the 4 is a 5, which forces that 4 up 1. So to 3 significant figures, our answer is 0.495. Now to work out C, which is the y-axis intercept, we can input one of these coordinate point pairs we know, either minus 0.7 and 0, or 0.21 and 0.45. We can input either of those for log base 10 of L and log base 10 of t respectively. I'm going to suggest we go for minus 0.7 for log base 10 of L and 0 for log base 10 of t, just because having the number 0 to substitute in tends to be the easier choice. And so if I pick this coordinate pair to substitute in, so for the x, if you like, minus 0.7, and like the y value being 0, we'll get this. So in terms of y equals mx plus c, 0 equals gradient times minus 0.7 plus c. And just to add in the colour coding, this is blue, and that's going to be the purple. So if we actually just work out what 45 over 91 multiplied by minus 0.7 is, which you can do here really easily, we get that 0 equals minus 9 over 26 plus c. So if I then add that to both sides, c obviously must be positive 9 over 26. So then we've got essentially what we need for the full model. We've got what c is, so in other words, we've now got what log base 10 of a is. And then from there, we can unpick this to work out what a itself is. And so c is 9 over 26, which is the same as log base 10 of a, because that is what c is. So we can now do 10 to the power of both sides. If I do 10 to the power of log base 10, one will undo the other, in the same way that doing e to the power of something to the natural log, one will cancel the other. So if I raise both of these to the power 10, like so, then this 10 and that log base 10 will cancel. So in other words, a is just going to be 10 to the power 9 over 26. So if we try this here, 10 to the power 9 over 26, and press equals, we're going to get 2.218, and that 1 will round up to a 2 because next to it is the 8. So again, to three significant figures like we're asked, we're going to get 2.22. So now we've got A and we've got B, so we can now put these back into the model as required, as it's asked us to do. So using this model here, t equals AL to the power B, this now becomes the following. We've got t equals 2.22 multiplied by L to the power 0.495, because you know that B is 0.495 and A is 2.22. Part C, with reference to the model, interpret the value of a constant A. This can be quite off-putting, this, because it's not so obvious what to do. Well, A is 2.22. T is obviously the time for one swing, and L and B were not told. So what I could think about here is, well, if L were the easiest, most simple thing it could be, which would be 1, then 1 to the power of anything would stay fixed as 1. And so basically, if we had a string length or whatever it is being held onto it, whether it be a string or thread, whatever the length of it is, if the length is 1, then A tells us the time taken for a swing of length 1 meter. So that's all we need to say for part C. It's just the time taken for a pendulum of length 1 meter to complete one swing. Question 11 is about graphs and the modulus function. So figure 4 shows a sketch of a graph of equation y equals mod of 2x minus 3k, where k is a positive constant. For part A, we need to sketch the graph of equation y equals f of x, where f of x equals k minus mod of 2x minus 3k. So in other words, f of x is k minus how y was defined here. We also need to give the coordinates of a maximum point, coordinates of any points where the graph cuts the coordinate axes, and that's all we need for part A. So I've made a little box down here where we can do our sketch. So first of all, if this is the graph of y equals mod of 2x minus 3k, let's first of all imagine if f of x was just simply just minus mod 2x minus 3k. If that were the case, then f of x would just be a reflection of this graph in the x-axis. So the graph of f of x, if it were just minus this modulus, the graph of it would look something like this. I'll come to the k, of course, in a moment, but just build it up step by step. So the graph of minus mod 2k minus 3x, as I've said, will be a reflection of this graph in the x-axis. So rather than being a positive v like this, it will now look like an arrow facing the other way around. The coordinates of the y-axis intercept, well, the y-axis intercept is given when x is equal to 0. So for this one here, for y, when x is equal to 0, so when x is equal to 0, I get y is mod of minus 3k, which is positive 3k. So because I've reflected this in the x-axis, that now becomes minus 3k, and this value here, where y is equal to 0, is obviously where 2x minus 3k is equal to 0. If I rearrange that and solve that linear equation, 2x must be equal to 3k. In other words, x must be 1.5k or 3k over 2. So we can label in these points. But now, I need to consider this k. So, because f of x is actually k minus 2x minus 3k all modded, I can consider f of x as being this minus mod 2x minus 3k plus k. So imagine k being added to this. That would have the effect of moving the entire graph up k units in the y direction. So imagining k coming into play, we'll go up by k units. So rather than the y-axis intercept being negative 3k, it'll now be 1k higher. 1 higher than minus 3k is minus 2k, and the coordinate of the maximum point is unchanged, well, the x-coordinate at least. That's at 3k and 2. So going back to the coordinates of a maximum, well, when x is 3k over 2, the modulus bit just vanishes. I'm just left with y being equal to k. So the coordinates of a maximum are when x is equal to 3k over 2 and y is equal to k. Secondly, the coordinates of any points where the graph cuts the coordinate axes, we've got these two x-axis intercepts here, as well as, of course, the y-axis intercept, but we've already labelled that on as minus 2k. So if I label in these two green points here, then we now have actually two cases to consider. So obviously we need to solve when it crosses the x-axis. It's when f of x is equal to 0. So I'm going to set k minus mod 2x minus 3k all equal to 0. If I now add this modulus to both sides of the equation, I can see that k must equal mod of 2x minus 3k. So now what I'm going to consider is that my x value is actually on the right-hand side of that red dot. So if I imagine that actually I'm looking at this side of a graph here, then 2x is going to be bigger than 3k. So in other words, this modulus, what's inside it, will be positive. So then k will just be 2x minus 3k. Because if 2x is bigger than 3k, the mod of this, because this is positive anyway, is just itself. If I now add 3k to both sides, I get that 4k equals 2x, then dividing by 2, x would equal 2k. So this point here is where x is 2k and y is equal to 0. The one on the other side would be the scenario when a 2x is actually less than 3k. Because this is where the mod flips. This is where the mod just flips the other direction. And so if 2x minus 3k itself is negative, the modulus of that will be the negative version of itself. So the second case, if we're looking at this side, will be when k is equal to minus 2x minus 3k. Now if I expand these brackets and simplify, this is the same as saying when k is equal to minus 2x plus 3k. If I add 2x to both sides and subtract k, I can see that 2x must equal 2k, then halving everything, this solution is when x equals k. So this point here is where x equals k. Now there's an easier way, in my opinion, of working that second point out. If this vertex here is when x is at 1.5k, and I can find this point first, which is 2k, then between this vertex, this tip, and this root, there's a difference of 0.5k. So that's a gap of 0.5k. Using symmetry, there'll be a gap of 0.5k on the other side as well. So 3k over 2, take away k over 2, take away half a k, would leave you with just 1 whole k. So you could have used symmetry as well. So we've now done part A thoroughly. We've labelled the maximum point and we've got all the intercepts of the axes labelled on. Part B, we now need to find, in terms of k, the set of values of x for which k minus 2x minus 3k all modded, in other words this graph here in blue, is greater than x minus k. So I'm going to add on this one. This will be a straight line graph with gradient 1, y-axis intercept of minus k. So I'm going to draw this one on in a purple straight line. I apologise, this graph is looking a bit congested, so it's hard to make out what's going on here. So if you listen to me carefully, I'll try and talk you through it as best as I possibly can. Apologies if I don't do well enough, but I'll do my best. So, as I say, this is congested. I'll talk through what these coordinates actually are in a second. So, what to do first? So, I want where the blue line, where f of x is higher than x minus k. In other words, greater than. So, the region I'm wanting is this bit here, which is above the purple, and also this tiny section here, which is also above the purple. So, it's just this tiny bit of the blue V I'm wanting, which I've highlighted in purple. So there's two different cases. One case, of course, is where x is going to be greater than 3k over 2 on the right hand side of this red maximum. The second case will be when x is less than 3k over 2, where we're looking on the left-hand side of this maximum. So taking it one step at a time, one case at a time. What if 2x minus 3k was greater than 0? So what I mean to say here is not so much the modulus of it, because the modulus is always going to be greater than 0, but what if 2x minus 3k itself was bigger than 0? So I've corrected it there. I've taken away the modulus signs. So if 2x minus 3k were greater than 0, what I'm trying to say there is if 2x were greater than 3k, then what's in this modulus would be greater than 0. So in that case, the equation to be solved would be the following. What would need to be solved, case B of course, is when what's in the modulus is less than 0. But for case A, what would need to be solved would be f of x, which would be k minus 2x minus 3k. So if this is positive, then it's its own modulus. So these modulus signs are the same as just normal brackets in that case. So if I simplify this by removing the brackets, I'll get k minus 3k, which will be 4k minus 2x. So I've got 4k minus 2x equals, it must be greater, sorry, than x minus k. I can then simplify this. I can then perhaps add 2x to both sides, and then add k to both sides as well. So that will give me that 5k must be greater than 3x's. But if I divide everything by 3, I can then see that x must be less than 5k over 3. The second case, if what's in these modulus signs is less than 0, then the modulus of this, if I'm taking the modulus of something which is negative, the modulus will take this thing which is negative and multiply it by minus 1. So if this is negative, then f of x will be k minus this here multiplied by minus 1. So I'll be wanting to solve k minus 1 times all of that. When is that greater than x minus k? So simplifying this left-hand side, undoing these minuses and all this awkward thing, it's going to become this. I'm going to get minus 2k plus 2x must be greater than x minus k. So then if I simplify this, I'll then get minus 2k plus x, just by taking an x on both sides, must be greater than minus k. But if I add 3k to both sides, so I add 2k, rather, I mean to say, and give x must be greater than k. So in putting this all together, as a question saying, giving an answer in set notation, I'm going to have the following. I'm going to get it so that x is such that x is less than 5k over 3, intersected with, and essentially grouped with x, such that where x is greater than k. Now, because this is an overlapping of two regions, in my opinion, even though the question asks us to give it in set notation, we could just combine this into one single interval, just one single range, as you can see here. Clearly we want x to be in between k and 5k over 3 exclusive. So we could put this into one inequality if we wanted, which would also be acceptable. So we could also say, if we wanted, x such that x is greater than k, but less than 5k over 3. Finally, for part C, we need to find, in terms of k, the coordinates of a minimum point of the graph with this equation, y equals 3 minus 5f brackets half of an x. This looks nothing like the equation we have for f of x, so what we're going to do is, what I'd suggest we do, I should say, is to start from what we know and build it up one step at a time from the f of x we know to the equation which we need, which is written here. So, what would f of half of x look like first of all? We've got what f of x is. F of half of x would look exactly the same, but any instance of x is going to be replaced with half of an x. So f of half of an x, for k stays the same, you get k minus, for 2x becomes 2 lots of half of an x, minus 3k stays as it is. 2 lots of half of an x, of course, is just one whole x. So that simplifies to k minus x minus 3k. I started with thinking about the half x first because I'm going to follow an order essentially the same as BIDMAS here. So start with inside the brackets first. Afterwards, what I'm going to do is look at outside the function brackets. The next thing is this -5. So now what I'm going to do, I'm going to take f of half of an x and multiply all of that expression by -5. I'm then going to add on that 3 after. Remember, multiplying comes before addition in BIDMAS. So next, let's think about this -5. So -5 multiplied by f of half an x will be all of this here multiplied by 5. So that's going to be 5 lots of k, sorry, minus 5 lots, because I'm multiplying by -5, almost forgot to say, brackets, k minus mod x minus 3k. Now can I expand out these brackets? So I've got -5 multiplied by minus this mod, so that will give me positive 5 lots of mod x minus 3k minus 5k. The final step now to go to the graph y is to take -5f half of an x and to add on this 3. So if I do this as a final step, take this and just add on 3 to it at the front, or at the back if you prefer, I'm going to get 5 lots of x minus 3k, all modded, minus 5k, plus an extra 3. So in terms of a modulus part, I've got 5 lots of a modulus of x minus 3k minus 5k plus 3. Now we've got this fully simplified equation, we can now consider where the minimum point of this graph is going to be. Well, the modulus of something can only ever be non-negative. The smallest it could ever be is 0. So the minimum point here is when the modulus of this is going to be equal to 0. This modulus will be equal to 0 when the stuff inside it is equal to 0. So when is x minus 3k equal to 0? That equation's easily solved. That's just when x is equal to 3k. So the minimum is going to happen when x is going to be equal to 3k. When x equals 3k, this whole thing vanishes, and then I'm just going to get that y equals just this minus 5k plus 3, which is left over. I've wrote it as 3 minus 5k, just putting the positive 3 first. So that's how I could write it, or I could write it as a coordinate pair. So I could also give my answer like this, 3k, comma, 3 minus 5k. Question 12 is an integration by substitution question. So this time we're told what substitution to use. So using substitution, u is 1 plus root x to show that this integral here can be transformed into this integral here, all in terms of u, where p and q are constants to be found. Well, the general idea of substitutions is to go from having something all in terms of one variable to having something all in terms of the other. So in this case, we want to remove all instances of x and replace them all in terms of u. So let's set to work doing this step by step now. So first of all, I'm going to rewrite this u as being 1 plus x to the half, because square root of x in index form is x to the 1/2. So that's an easier way of working out what things integrate and differentiate to. One thing I can see here looking at this integral is I'll need to replace this x in terms of u. So what I'll need to do is to get what, first of all, x to the half is in terms of u. So if I take away 1 from both sides, x to the half, or root x, must be u minus 1. But if I square both sides, therefore x must be u minus 1 all squared. One thing I'll always need to do as well, almost forgot how to talk there, would be to take the derivative of du by dx. So if I differentiate u with respect to x, obviously the 1 will disappear. X to the half will become half x to the minus half. I can then take this expression and rearrange this to see what dx is in terms of du. So essentially I'm going to multiply through by dx, then double both sides, and then divide through by x to the minus 1/2. That'll give me that dx must be the same as 2 lots x to the positive 1/2 lots of du. So now I've got dx in terms of du, and also I've told what 1 plus root x is. I'm told what that is in terms of u as well. So it would appear that I'm pretty much done. One thing I need to do as well, though, is to work out what p and q are. So P and Q relate to these limits here. So these are limits for X, these are limits for U. And we have here essentially a recipe how to change from X units into U units. So let's get a table up and ready. So when X is equal to 16, which I'm going to highlight in pink, which is going to correspond to this pink P, when X is 16, the corresponding value of U will be 1 plus the square root of that 16. And the square root of 16, of course, is 4. So the corresponding U value for when X is equal to 16 will be 1 plus the square root of 16, which is 1 plus 4, which is just 5. In the same way, when X is 0, which I'm going to put in purple, that's going to relate to this limit P. So when X is 0, U will be 1 plus the square root of 0, which of course will just be 1. So therefore P equals 1. So we've got dx in terms of du, we've got x itself in terms of u, and 1 plus root x is itself u. So it would appear that we're pretty much good to go. So therefore, this first integral becomes the integral from 1 up to 5, u minus 1 squared all over u multiplied by 2x to the half du. So there's a snag. We've still got an x to the half remaining, so it's not quite all in terms of u. So one thing I did mention up here, I could have done this earlier, or I can do it now. I'm choosing to do it now. I can replace x to the half with u minus 1. So just realise that x to the half is u minus 1. I can just replace x to the half with u minus 1. So that gives me my next line. So the initial integral is the same as this thing here. So now I've got u minus 1 squared multiplied by another lot of u minus 1. That's going to give me u minus 1 cubed, which is what I want. The factor of 2, which is what I want as well. And it's all over u. So this is in the exact form as what I wanted it to be shown to be. And so essentially I've done the question. Just neating it up in the final step, and we're done. In other words, q is 5 and p is 1. But it's a case of showing it, not just showing just one line of it. It's step by step to get the full marks. Using part A now, we're going to show that the integral from 0 to 16 of x over 1 plus root x is a minus b ln 5, where a and b are some constants to be found. So this is what we had from before. So now what we can do is we can actually expand out this numerator algebraically. So expanding out 2 lots of u minus 1 all cubed. You could use a binomial expansion if you want to, or just do it manually, but take your time, you should get this. By the way, alternatively, you could have factorised out the 2 before the integral. I left it in on the inside this time because multiplying by 2, I don't know if it was too hard, but it's optional. So, going to get 2 lots of u cubed, basically u cubed times 2. I'm then going to get minus 3u squared using the binomial expansion, but times 2, hence minus 6u squared, and plus 6u minus 2 all over u. So the most important thing I'd suggest for you at home to realise, and just to convince yourselves of, just make sure you're okay with seeing that this is one and the same as that. If you're okay with that, then the rest should follow a bit nicer. So the next step now, with this integral, I can take all of this numerator and divide everything by u. So the next step, this integral now becomes 2u squared minus 6u plus 6, and minus 2 all over u, I can just write as a single fraction like this. So I'm now ready to integrate it. So 2u squared integrates to 2/3 u cubed, minus 6u integrates to minus 3u squared, 6 becomes 6u, and minus 2 over u, because 2 is double the derivative of u itself, that becomes minus 2 lots of a natural log of u. So now we're just putting the limits of 5, then minus off what we get when we use the lower limit of 1. So 2/3 u cubed, when x is 5, becomes 5 cubed, which is 125, times 2/3 gives 250 over 3, minus 3u squared means minus 3 times 25, hence minus 75, plus 6u is 30, because 6 times 5 is 30, minus 2 ln u means minus 2 ln 5. Then minus off, when we input the lower limit of 1, 2/3 u cubed becomes 2/3 times 1 cubed, hence just 2/3. Minus 3u squared is just minus 3, because u squared is just 1, because 1 squared is 1, of course. And 6u means 6 times 1, which is 6. Now, I don't need to put minus 2 ln of 1, because log of 1 to any base will always be 0. So if I wanted to, I could have pressed or typed in minus 2 ln of 1, but it wouldn't have changed anything at all. The only thing we now need to do is to just type this in carefully, just the numbers. We need to leave it in this form here. So we know that the minus b ln 5 will be the minus 2 ln 5. So the only thing we need to do is just to add these values together, these fractions and constants. So I've got 250 over 3 minus 75 plus 30. Then I'm minusing off, in brackets, all of 2/3 minus 3 plus 6. So I get 104 over 3. So therefore my final answer in this form is 104 over 3 minus 2 ln 5. Question 13, we've got a curve C defined parametrically as follows. We've got x is sine 2 theta and y is cosec cubed theta, where theta is defined in between 0 and pi over 2. We need to find an expression for dy by dx in terms of theta. This is a standard result. We need to remember that to find dy by dx when equations given parametrically is we differentiate y with respect to the parameter and divide that by what we get if we differentiate x with respect to the parameter. In this case, the parameter is theta. Even though these aren't fractions, you can think of them like fractions. Essentially, the thetas will cancel, just giving you overall dy by dx. So dy by d theta is going to be the harder thing to differentiate. So how am I going to differentiate cosec cubed theta? Well, right now I'd be going straight to the formula book to see if there's any results for cosec cubed, cosec squared, cosec anything. You won't come up with much. There is a result for differentiating cosec theta. So cosec cubed, no good. So what I may as well do is split it into a single cosec multiplied by cosec squared. So this, of course, is a product. So I could use the product rule for differentiation. So my first function, I'll call u, I'll call that cosec theta. The second function, v, I'll call cosec squared theta. Now if I check the formula book, cosec theta does differentiate to minus cosec theta cot theta. But you'll find no result if you go hunting high and low for what cosec squared theta differentiates to. So this one we'll need to work out manually. So at the bottom, let's just do this, how to work out the derivative of cosec squared theta. So again, we can use a product law for differentiation. So if I just write this as cosec theta times cosec theta, we can now set u to be cosec theta and v to be cosec theta. If I differentiate cosec theta, I get minus cosec theta cot theta. So if I were to differentiate this, what I'd do, I'd differentiate cosec theta and hold cosec theta constant. So the derivative of cosec theta is in the brackets, then multiplied by cosec theta. And then the same thing again with the roles switched. Now I hold the first function constant, so cosec theta hold constant, then differentiate the second. So again, I get this derivative in this bracket. But because both functions are one and the same thing, essentially I get the same thing twice. So what I'm going to get here is two lots of negative cosec squared theta cot theta. And that is the derivative of cosec squared theta. So now we know what the v dashed is here, so there's nothing now stopping us from applying the product rule for differentiation. So to differentiate cosec cubed theta now, essentially I just do the cross multiplication of u v dashed and v and u dashed. So the derivative of cosec cubed theta is going to be, I hold u constant multiplied by v dashed, which is this one here, cosec theta multiplied by minus 2 cosec squared theta cot theta. Then I add on when I keep v constant and differentiate u. So I'm going to add on cosec squared theta multiplied by minus cosec theta cot theta. But again, you'll see we're going to get the same thing again duplicated. We're going to be getting, from this one, minus 2 lots of cosec cubed theta cot theta, and then from this one, minus another 1 lot of cosec cubed theta cot theta. So overall, we've got minus 3 lots of cosec cubed theta cot theta. That's dy by d theta, which is by far the harder piece to find the derivative of. dx by d theta is much easier. So if x is sine 2 theta, I can use a chain rule to differentiate that. Sine differentiates to cos, so it becomes cos 2 theta, but because of this constant 2 in the function, I need to put that on the front. So dx by d theta just becomes 2 lots of cos 2 theta. Piecing the blue and red together, dy by dx is therefore the blue on top of the red. In other words, dy by dx is just minus 3 cosec cubed theta cot theta all over 2 cos 2 theta. For part B, we're now going to find the exact value of the gradient of a tangent to C at the point where y is equal to 8. Well, y itself is cosec cubed theta. So y actually appears in the derivative function as well, because cosec cubed theta is y. So let's start off by just setting cosec cubed theta to be equal to 8, because that is what y is equal to. So what I'm going to suggest we do first of all is to cube root both sides. That will then give me that 2 is cosec theta. Now cosec is 1 over sine. So if I reciprocate both sides of this, just basically flip them on their heads to find the reciprocals, this will now become a half, and the reciprocal of cosec is sine. So I'm trying to solve when sine theta is equal to a half. This is an exact trig value, but you can use your calculator if you want to. If I were to do arc sine, or sine minus 1 of this, you should see that in radians, theta is going to be pi over 6. From that, now I know that theta is pi over 6, I can work out what cot theta is. So cot theta just means 1 over tan theta. So we can work this out. So if I do 1 over tan theta, 1 over tan, making sure I'm in radians. Look, r for radians, that's okay. So I'm going to do all that over pi over 6. I'm going to get root 3. So therefore, cot theta is root 3. And in the same way, I could work out 2 lots of cos 2 theta as well. In fact, why not? I'll do that as well. So 2 lots of cos 2 theta, that's going to be 2 lots of cos. If I double pi over 6, that's going to be pi over 3. So 2 lots of cos pi over 3, that just becomes 1. So therefore, well, 2 cos 2 theta is 1. So just cos 2 theta on its own, sorry. Cos of pi over 3 is just simply 1/2. So now, if I were to substitute these values in, so I know now what everything needs to equal. So this bit here equals 8. This is root 3, and that becomes 1/2. Then dy by dx, where y is equal to 8, is minus 3 times 8 times root 3, all over 2 times 1/2. But 2 times 1/2, of course, is just 1. So it's just going to be the numerator, essentially, which is minus 3 times 8 times root 3. Minus 3 times 8 is minus 24. So the final simplified answer in exact form for the gradient when y is equal to 8 is it's equal to minus 24 root 3. Question 12 is a practical application of differentiation. So water's flowing at a constant rate into a large tank. The tank is a cuboid with all sides of negligible thickness. The base of the tank measures 8 by 3 meters and the height of it's 5 meters. There's a tap at point T at the bottom, as shown in figure 5 here. At time 2 meters after the tap's been opened, the depth of the water in the tank is h. Water's flowing into the tank at a constant rate of 0.48 cubic meters per minute, but also water's modelled as being lost from the tank. It's leaving the tank through this tap at a rate of 0.1 multiplied by the height cubic meters per minute. Show that according to the model, we've got this differential equation. So this can be quite overwhelming. It's where on earth do we even start? Well, if we can work something out, do work that something out. So cubic meters, that's talking about volume. And this is a cuboid. So what we could do is work out the volume of this cuboid, or the volume of water, I should say, in this cuboid. The volume of water inside will be length times width times height, 8 times 3 times h. So the volume of water will be 24h. Because this is a differential equation, what we could do is we could find either dv by dh, or we could do dh over dv. So we'll come to that in just a second. We're also told water's flowing into the tank at a constant rate of 0.8 cubic meters per minute, but also water's leaving it at 0.1 h cubic meters per minute. So this is actually telling us what dh by dt is. In plain English, dh by dt just means the rate of change of the height per unit time, in other words, per minute. So this is what dh by dt is. Here though, so we're talking about volume, aren't we? So this is going to be dv by dt, I mean to say. So dv by dt is going to be plus 0.48 because it's increasing by 0.48 cubic meters per minute. But also, because it's losing water here, this part of dv by dt would be minus 0.1h because the water is being drained from the tap at that rate per minute. So putting these two pieces in red together, we can work out what dv by dt is. Essentially, dv by dt must be 0.48. That's the rate per minute of water going in, and this is a rate per minute of water being lost through the tap. So we need to find dh by dt. So this is a related rates of change question. We've got dv by dt. We could do finding another derivative relating v and h, for example this top formula here. So if I make h a subject, h is v over 24, I can now work out dh by dv. If I differentiate h with respect to v, then dh by dv will just become 1 over 24. The v will vanish. So now I've got dv over dt and dh by dv. By some combination, I can take these, multiply them together, and end up with dh by dt. So, in other words, dh by dt, although these aren't fractions, we can think of them in a way like fractions. dh by dt will be dh by dv multiplied by dv by dt, both of which we've now found. So we can think of it like a fraction in terms of dv at the top and bottom cancelling, just leaving us with dh over dt as required. So that's going to be 1/24 multiplied by this expression. So dh by dt is 1/24 times 0.48 and a 24th of minus 0.1h. So after multiplying and expanding these values here by 1/24, these values of course are going to become very small indeed. We get dh by dt is 0.02 minus 1/24h. We want to show this is true. So the final step here, we just need to multiply both the left and right hand side of this equation by 1200. And if we do that, we arrive at our result which we wanted to prove and show after all. Therefore, yes, it is true that 1200 dh by dt is 24 minus 5h. If you try this on your calculator, it does work. 0.02 times 1200 is 24, and 1/24 of 1200 is 5. Part B, now what we need to do is, using the model from Part A, show that h equals a plus b e to the power minus kt, where a, b and k are some constants to be found. So just remembering the model from Part A, which I'm going to put in red, from Part A, we showed this was true. So what we can do here is separate out the variables, have one side in terms of dh and the other side in terms of dt and just t. So I could multiply both sides by dt to get the dt onto the right hand side and eliminate it from the left, and also I could divide both sides by 24 minus 5h so that I get 1200 over 24 minus 5h on the left-hand side, and over here, dividing it by 24 minus 5h will just leave me with a 1. Well, it will become just 1 dt, because I'm multiplying by dt. So in one move, I can think of it as multiplying by dt and dividing by 24 minus 5h on both sides. In other words, this expression in red can be transformed to this. 1200 dh all over 24 minus 5h equals dt. We can now add integral signs to both sides and essentially just integrate both sides. So the final thing to say is we've now got this. Now, this one here, the numerator is not at all the derivative of the denominator. 24 minus 5h would differentiate to minus 5. So what I could do here, I could divide this by minus 5 to get minus 240. So if I rewrite 1200 as minus 240 times minus 5, I can rewrite the integral like this. So minus 240 lots of this integral equals the integral of dt. Because now the numerator is the derivative of the denominator, this will now become minus 240 ln mod 24 minus 5h. And the integral of dt will just become t. And then of course we need to add on the constant of integration. So in terms of the constant of integration, we need a boundary condition, or some more information, which we are told. We're told that when the tap was opened, the depth of water in the tank was 2 meters. The tap was opened, the time starts after the tap was opened. So that's saying when the time is 0, h is 2. So if we substitute those in, time being equal to 0 will just mean that we have something which equals c. So in other words, substituting in h being equal to 2 here, that'll give us ln of 24 minus 10, that'll become ln 14. So that'll give us at minus 240 ln of 14, that must equal c. So therefore, this here equals t minus 240 ln 14. So if I were to add 240 ln 14 onto both sides of this equation to get t as a subject, essentially t must equal this. T must equal minus 240 ln mod 24 minus 5h plus 240 ln 14. If I now factorise out this 240, I get that t equals 240 ln of 14 all over 24 minus 5h, just using laws of logs here. One log minus another log is the same as log of that one thing divided by log of the other. So what to do next? Well, if I now divide both sides by 240, I get that t all over 240 must equal the natural log of the mod of 14 all over 24 minus 5h. If I now raise both sides to the power of e, and I'll get t over 240 equals 14 all over 24 minus 5h. At this stage, I'm going to bail and actually write down manually because there's not enough space to squeeze it on. If I tried to, it'd just make it counterproductive. So if I think of this e to the power t over 240 as a fraction in its own right, I can now solve this by cross-multiplying. So I can do 14 times 1 and say that's equal to 24 minus 5h times e to the power t over 240. So in other words, the next line is to say that we've got e to the power t over 240, all that times 24 minus 5h. That must equal 1 times 14, which is 14. Then I expand this out, I get 24 e to the power t over 240 minus 5h e to the power t over 240. That'll all equal 14. I want to get h on its own, because I want it to be h as a subject. So now if I add 5h e to the power t over 240 to both sides, let's get that as a subject, 5h e to the power t over 240 That's the same as 24 e to the power t over 240 minus 14. So now I'm going to divide everything by e to the power t over 240. So if I do that as the next step, divide everything by this power of e, and I get 5h equals 24 minus 14. Then that divide by e to the power t over 240 becomes e to the power minus t over 240. Then divide everything by 5. So h is going to be 24 minus 14e minus t over 240 all over 5. Now I want it in this form here. So 24 divided by 5, of course, is 4.8. So I'm going to give a as 4.8. Then minus 14 over 5, that's the same as minus 2.8. That's minus 2.8. E minus, I've got a minus sign, good. Then the constant times t, I'll call the constant 1 over 240 to make it explicit, but I'm writing it exactly the same form as what the examiner wants it in. So therefore, that's what h is. Exact fractions would have been okay as well instead of decimals here. So instead of 4.8 and 2.8, you could have put exact fractions too, of course. Finishing off question 14 is part C. So we're told here that the tap remains open. We need to determine, using this model, whether the tank will ever become full, giving a reason for our answer. So from before, we know that dH by dt is 24 minus 5h all over 1200. So obviously 24 minus 5h, that's going to be constant for anything where h is all the way up to 4.8. So clearly here, where the height's really small, nowhere near 5, it's going to be increasing and increasing. So because of this expression for what dH by dt is, we need to then work out from this, or deduce, that water will keep rising until dH by dt equals 0, after which time it will even off and then begin to fall, after which, assuming dH by dt then becomes negative, of course. So dH by dt is 0. The critical point is when dH by dt is 0, and that's when 24 minus 5h, the numerator, is equal to 0. If I add 5h to both sides, then divide by 5, I can see that h will be 4.8 and the water stops rising. However, if we get to 4.8 and the water stops rising, then it'll never quite get full, because 4.8 meters isn't quite as high as 5 meters. So with reference to the diagram, it's 5 meters high. So to conclude, because 4.8 is less than 5, the tank will never become full. 15 part A, express 2 cos theta minus sine theta in the form r cos theta plus alpha, where r is greater than 0 and alpha is between 0 and pi over 2. Give the exact value of r and the value of alpha in radians to 3 decimal places. So this here is a compound angle formula question. So we need to put this here, which is in terms of cosines and sines, into a single cosine. So this is in terms of thetas and alphas. So the compound angle formula for cos of theta plus alpha, I need to remember, is as follows. Or if you don't remember that, then it is in the formula book. So we need to just assign, I would suggest theta as being capital A and alpha being capital B. So I just underline capital A in blue, like I've done for theta, and in red, underline B, like I've done for alpha. Now we want to have cos of alpha plus theta, add them together. So that's the top symbol here. So I'm just going to talk you through how to use a formula book, because sometimes these upside down symbols can look confusing. All you're needing to do is working out what symbol you're wanting to use, whether it be the top symbol or the bottom symbol. Because we're wanting to add and adds on the top, we're interested in the top symbols only, so we just essentially delete the bottom symbols. So if I delete this minus and that positive, you hopefully can see now that the formula we're wanting is cos A plus B is cos A cos B minus sin A sin B. So replacing A for theta and B for alpha and multiplying all of this by r at the front, this is going to become the following. We're going to get r cos theta plus alpha is r lots of cos theta cos alpha minus sin theta sin alpha. I can now rearrange this somewhat to work out the components of both cos theta and sin theta and then equate them to what they need to be. So if I just rearrange this a tiny bit here, I get r cos alpha at the front times cos theta, then minus, and this will become, when I expand it all out, r times sin alpha minus r sin alpha times sine of theta. Now, in terms of cos theta, I've got r cos alpha, lots of cos theta. But in terms of actually what I need to have two lots of cos theta. So r cos alpha, for it to work and for it to equate properly, r cos alpha must be worth 2. In the same way, the component of sin theta is minus r sin alpha. So minus this bit of sin alpha must equal minus that bit of sin theta. I can imagine this as being an invisible minus 1 here, essentially. So that's a minus r sin theta. This is a minus 1. So essentially, equating sin theta components, I can see that r sin alpha must equal 1. Don't worry about the minus, that's already accounted for both here and there. So essentially now we've got two simultaneous equations we can solve. So we've got that r sin alpha is 1 and r cosine alpha equals 2. I'm going to call one equation A and the other one B. The first thing I can do is one equation divide by the other. So if I just do A divided by B first, r sin alpha divided by r cos alpha, r divided by r will cancel, and sine over cos, that will give me tan alpha, which is a half. I can therefore do arctan to work out what alpha is, correct to 3 decimal places. So alpha will be tan minus 1 of a half, which would round to 0.464. I can also now, these equations, square them and then add them. If I do that, I'm going to get r squared sine squared alpha plus r squared cos squared alpha equals 1 squared plus 2 squared, which gives 5. Now, if I were to factorise out the r squared from this left-hand side, I'd get that r squared brackets sine squared plus cos squared equals 5. But sine squared plus cos squared, of course, equals 1. So what I'm trying to say here, without giving you an extra line of working, is this just simplifies very simply into just r squared equals exactly 5. Because a sine squared plus cos squared, which should factorise out, would become 1 anyway. Square root both sides, r must be equal to root 5. I'm not going to give that as a decimal because the question is asking me to give r in exact form. So that's r in exact form, that's alpha to 3 decimal places, so therefore, piecing all this together, I can see that 2 cos theta minus sine theta must be the same as r root 5 cos of theta plus alpha, which we worked out was 0.464. Now we're getting on to the application of that question. So figure 6, we've got a cross-section of a water wheel, and the wheel is free to rotate about a fixed axis shown here. The point P is at the end of one of the paddles of the wheel, as shown in figure 6. The water level is assumed to be horizontal and of constant height. The vertical height, capital H meters, of this point P above the water level is modelled by the equation h equals 3 plus 4 cos 0.5t minus 2 sine 0.5t, where t is the time in seconds after the wheel starts rotating. So using the model, we need to do part B. So first of all, we need to remember the model. So from before, what we had from part A was we showed that 2 cos theta minus sine theta equals root 5 cos theta plus 0.464. So we need to remember what this model actually was. This is what we show the model from part A to be equivalent to, but here we're talking about thetas. Here we're talking about t. So the first thing to mention is here we're talking about theta. So I need to adapt what we had from part A to make it match to part B step by step. So the first thing to notice is the input here isn't theta. This as it stands is a function of theta. So if I were to call this just f of theta, I'm actually wanting now to find a function in terms of t. If I just switch theta in terms of t, then f of t would be this. Exactly the same looking thing, but theta just replaced with t. So if I input t here, t appears elsewhere. I don't want a function of t though, I want my input to be 0.5t. So in the same way, if I switched theta for t, then the input theta just switches for t. If I now switch t for 0.5t, each instance of t here in green will just become an instance of 0.5t in yellow. So f of 0.5t is this expression here, which of course in our model would become root 5 cos of 0.5t plus 0.464. I'm building it up step by step according to the rules of BIDMAS. So I'm starting inside the function brackets first, and now what I need to do is to spot that instead of having a 2 cos and a minus 1 sine, I need 4 coses and minus 2 sines. So essentially what I need to do is all of these components I need to double. So I need to go in my next step from f of 0.5t to 2 lots of f of 0.5t. So I'm just going to double everything through. So then, this is the initial equation, the new model from part A. I'm just going to double the root 5, double the magnitude, so it becomes 2 lots of root 5 cos 0.5t plus 0.464. So this bit here is almost the same as this model for h. The only thing I'm missing is this 3 at the front. So if I just add 3 on now as a final step, that'll now give me a model for 3 plus 2f of 0.5t. So if I now just put 3 plus at the front of all this, I now arrive at this expression here, and in terms of the model we had from part A, to adapt that finally, all I need to do now is just to have this with an extra plus 3. So this is going to become finally 3 plus 2 root 5 cos of 0.5t plus 0.464. So we're pretty much done in terms of finding this model. So if we just now have a look at this middle piece here, I'm going to highlight this in red. I need to spot that this is exactly the same as this formula for h. So in other words, this is h of t, and that is what h of t is using our adapted model from part A. So therefore, h in this more useful form, just in terms of a single cosine rather than a mixture of sines and cosines, is 3 plus 2 root 5 cos of 0.5t plus 0.464. We can now use this model to finally answer part B essentially. So for part B, we need the maximum height of P above the water level. So the maximum height of P, h max, 3 is a constant, 2 root 5 constants. Cosine is going to vary. The maximum value of the cosine function is a value of 1. So h is going to be maximized when cosine of this is equal to 1. So B part 1, we're going to have h max when cos of that equals 1. So the maximum value of cos is 1. So if I just input 1, or just substitute in fact 1 in place of this, then h max will just be 3 plus 2 root 5 times by the maximum cos, which should be a value of 1, which just gives us 3 plus 2 root 5 meters. And as a decimal, if you wanted to, you could give it as 7.47 meters. For B part 2, we want the value of t when the maximum height first occurs, given the answer to 1 decimal place. So this maximum obviously occurs, we said here, when cos of 0.5t plus 0.464 equals 1. So just returning to that point again, we can now think about when that happens. So when is cos at a maximum? Well, cos is equal to 1 when this is equal to 0. Cos of 0 is equal to 1. But of course, we want the first value of t when this happens. If this were equal to 0, then t would have to be negative, because I'm already adding 0.464 onto it. So the next value we'd want in degrees, I'm using degrees because it's more familiar, it'd be 360 degrees. So actually, it might be that 0.5t plus 0.464 is equal to 2 pi, which is what it is in radians. So I need 0.5t plus 0.464 to equal 2 pi. If I now double this to get what an actual whole t would be, in fact I'll rearrange, I'll take away 0.464 first. I get that 0.5t equals 2 pi minus 0.464. Now if I double everything, I get that t equals 4 pi minus 0.928. Then because I need this in terms of a decimal, and I just need to convert this into a decimal answer. So if I type in 4 pi minus 0.928 on the calculator, in fact, may as well do this now. So 4 shift pi minus 0.928. That gives me 11.6. So to one decimal place, it's going to be 11.6 seconds. Now let's have a look at part C of this question. So for part C, what we've got to think about now is in a single revolution of a wheel, P is below the water level for a certain period of time, capital T seconds. So according to the model, find this value of T, giving our answer to 3 significant figures. So from part B, we saw that a complete revolution is 11.6 seconds. Although diagrams can never, well, I wouldn't say never, because diagrams aren't normally drawn to scale unless they say they are. This one isn't to scale. It's not to say that a diagram should be wildly off. So I think it's fair to say here, the artists trying to insinuate, trying to hint to us that P is going to be underneath the water for a minority of the time. Look at this wheel. The majority of the circumference is above the water rather than below. So you're expecting your answer for how many seconds it's below the water to be only like maybe, I don't know, a quarter, a fifth, a third, but a minority fraction of our answer of 11.6 from before. So just bear that in mind so we can then sort of think about if our answer makes logical sense or not. So anyway, starting off with this question. The value of when it's above or below the water level. The critical value here is when the height's equal to 0. So what we could do is sub h equal to 0 and find the critical times when P is entering the water. That's basically when h is equal to 0. So if we just set h equal to 0, we've got 0 equals 3 plus 2 root 5 cos of 0.5t plus 0.464. If I now subtract 3 from both sides, this now becomes minus 3 equals 2 root 5 cos of 0.5t plus 0.464. If I now divide both sides of this by 2 root 5, I get that minus 3 all over 2 root 5 must equal cos of 0.5t plus 0.464. So this here is not just cos of theta or cos of t, it's cos of something quite awkward. So my tendency, my preference is to replace anything awkward that I'm taking sine, cosine or tangent of, and replace it with big X temporarily. So I'm going to call this big X for now. So I want cos of big X to be equal to minus 3 over 2 root 5. To find the principal value for big X, I can do arc cos of minus 3 over 2 root 5, and if I do that, I should find that the principal value of X is 2.306 radians. So on a cast diagram, this would be an obtuse angle. So I've labelled on this cast diagram the principal value 2.306. Cos here, this is a negative value. So the quadrants we're interested in looking for where cos might be is the S quadrant, where cos is negative, and also the T quadrant. I'm going to explain why this solution is 3.977. Essentially, time only makes sense if we go positive way round. And so this angle here, the positive way round, is 2.306. By symmetry, if I went the wrong way round, the size of this angle here, from the positive x-axis down through to t, the size of that would also be 2.306. So this green angle will be the full circle of the entire 2 pi minus, apart from, the 2.306. So essentially what I've done there is done 2 pi minus the 2.306, and we get 3.977. So that's why I get, to 3 decimal places at least, a value of 3.977 in the T quadrant. So now what we can do is try and solve. So therefore, either x is 2.306, or the second time, where the height of it's equal to 0, is where we have 3.977 radians. But we don't want it in terms of x, we want to work out the exact times. So if we now replace capital X with what capital X actually was in terms of times, we've got two equations to solve essentially, to find the critical times. So when is 0.5t plus 0.464 equal to 2.306? And also when is it equal to 3.977? I've run out of space, so these are ones for you to solve on your own, but hopefully you should get the answers that t for one of them is 3.684 and t for the other is 7.026. So this is about 3.5 seconds, that's about 7 seconds. So between here and here is a gap of 3.5 seconds. So either it's below water, then going above, then below, then it's all below. So either all this is below, and then this bit is above, or this bit is below water, and all the rest of it is above. Now, like I discussed earlier, it's going to be below the water for only a small fraction of the 11.6 seconds. So actually, between these two values here is about 3.5 seconds, so that sounds about right, about a quarter of the total time. So all we need to do now is to do 7.026 seconds minus 3.684 seconds to find the amount of time in between which the paddle is underneath the water level. So finally, it's going to be below the water for 7.026 minus 3.684, which is 3.34 seconds when given to three significant figures, which is what we're told to do. Finally, part D, the last part of the very last question. In reality, the water level may not be of constant height. Explain how the equation of the model should be refined to take this into account. So what might need to change here? Well, the 4 cos 0.5t and the 2 sin 0.5t, these are attached to the trig functions. So because these are trigonometric, which go up and down in waves, we can assume that the 4, the 2 and the 0.5 relate to the wheel itself. So this could probably be altered mechanically. So because this relates to the time could be altered by using the fuel differently or whatever. But actually it's this constant here, the 3, which is the giveaway. It's this constant 3 which might need to change. So for example, it might be a low tide or a high tide or who knows what, or flooding. So that 3 might need to be adjusted from time to time. And that's what we need to say for getting our mark. So something along these lines, the refining step needs to come from this constant 3. So essentially, we might just need to say the 3 term, the constant term 3, may need to be adjusted or refined after a certain time period. And that's all there is to it, really. That's all the questions done. Hope you found that useful. Thank you very much for listening. Feel free to leave me a comment, a like or subscribe, or any suggestions you might like to add. Hopefully constructive ones, please. So once again, sincerely thanks for listening, and I hope to see you soon.